In 2022, the James Webb Space Telescope pointed at a patch of sky that had been studied before. Not a new region, not an unexplored corner of the cosmos. A patch of sky that Hubble had imaged, that ground-based telescopes had catalogued, that astronomers had analysed for years. Webb looked at it with instruments 20 times more sensitive than anything that had come before, with a mirror 6.5 meters across, collecting light from the deepest reaches of the observable universe, with detectors cooled to temperatures colder than interstellar space, sensitive to infrared light that no previous space telescope could access. And what it found was not what the models said should be there. The galaxies were wrong. Not subtly wrong, not at the margins of what the predictions allowed. They were wrong in a way that caught the attention of the astronomers who spent their careers building the models those galaxies were violating. Massive galaxies, fully formed, containing hundreds of billions of stars, with mature stellar populations and structured morphologies, sitting at distances corresponding to redshifts of 6, 7, 8, 9, 10. Distances so great that the light reaching Webb had been travelling for more than 13 billion years. Distances representing a time less than 1 billion years after the Big Bang. Those galaxies should not exist, not in the models, not in the theoretical framework that cosmologists had spent 50 years constructing and refining and testing against every piece of observational data available before Webb launched. The models predicted that 1 billion years after the Big Bang, the universe should contain only the earliest, smallest, most primitive galaxies, proto-galactic structures still assembling their first stars, still accumulating mass from the surrounding intergalactic medium, still hundreds of millions of years away from the kind of organized, massive, evolved systems that Webb was finding in abundance. The galaxies Webb found were not proto-galactic structures. They were galaxies, old galaxies, galaxies with stellar populations implying hundreds of millions of years of star formation history in a universe that was itself less than 1 billion years old. Galaxies that appeared to have formed and matured and organized themselves into recognizable spiral and elliptical structures in a time frame that the standard model said was far too short for any of that to happen. John Mather, NASA senior astrophysicist, Nobel Prize winner in physics for his work on the cosmic microwave background radiation, one of the architects of the James Webb Space Telescope itself, described the situation with language that the scientific community does not typically use about its own models. He said, "It is a different universe than we thought." He said the galaxies we are finding should not exist, and that this could break everything we know. Not everything we think, everything we know. This is not a scientist who exaggerates. Mather shared the 2006 Nobel Prize in Physics with George Smoot for the discovery of the black body form and anisotropy of the cosmic microwave background radiation, measurements that confirmed the Big Bang theory and established the standard model of cosmology with precision that made it one of the most successful scientific frameworks in history. When a scientist of this background and this disposition says that what his telescope is finding might break everything we know about the universe, it is worth understanding precisely what is being found, and precisely why it is so difficult to accommodate within the existing framework. Tonight we are going to examine what Webb has found. The specific observations, the specific numbers, the specific ways in which the distant universe, the universe as it existed more than 13 billion years ago, appears to be different from what the best models of cosmology predict. And we are going to examine what this means, not in the sensationalized version that strips away the nuance, but in the honest version that is simultaneously more careful and more strange than any headline can convey. Before we begin, if you put this on because the night is long and you need something substantial to settle into, stay with this. What follows is worth the time. Let us start with the model. Because you cannot understand why the observations are disturbing without understanding what the model predicts and why the model has been so successful that disturbing it requires extraordinary evidence. The standard model of cosmology, often called lambda CDM for the cosmological constant lambda representing dark energy and cold dark matter representing the dominant form of matter, is the theoretical framework that describes the large-scale structure and evolution of the universe from the Big Bang to the present day. It has been extraordinarily successful. It predicted the detailed pattern of the cosmic microwave background radiation before it was measured with sufficient precision to test the prediction, and the prediction was confirmed to a level of accuracy that effectively rules out all but a small class of competing models. It predicted the statistical distribution of galaxies in large-scale surveys, the cosmic web of filaments and voids, and surveys found exactly this distribution. It predicted the abundance of light elements produced in Big Bang nucleosynthesis, the specific ratios of hydrogen to helium to deuterium to lithium, and those abundances were measured and matched. It predicted the accelerating expansion of the universe and identified it as requiring something like dark energy, a prediction confirmed by the discovery of the accelerating expansion through supernova observations in 1998. These are not marginal successes. They are precise, quantitative predictions confirmed by independent observations using different telescopes and different techniques and different physical principles. Lambda CDM is not a hypothesis that fits some data. It is a framework that fits essentially all the data collected across 50 years of modern cosmological observation, with quantitative precision that leaves very little room for the model to be wrong in any fundamental way. And yet, the galaxies Webb is finding in the early universe appear to be in tension with it. The tension is real. It is being taken seriously by serious scientists, and it is worth understanding in detail. The heart of the issue is galaxy formation. In lambda CDM, the formation of galaxies is a bottom-up process. Small structures form first and merge over time into progressively larger ones. This is called hierarchical structure formation, and it follows directly from the physics of how dark matter halos grow under gravity in an expanding universe. Small dark matter halos collapse first from the primordial density fluctuations of the early universe. Ordinary matter, gas, falls into these halos and eventually forms stars. Those halos merge with other halos, forming larger structures. Stars form, live, die, and enrich the surrounding gas with heavy elements. More stars form from the enriched gas. Over billions of years of this process, the small proto-galactic structures of the early universe grow and merge and evolve into the large organized galaxies we observe nearby. This process takes time. The specific amount of time is calculable from first principles given the measured parameters of the lambda CDM model: the density of dark matter, the density of ordinary matter, the expansion rate, the amplitude of the initial density fluctuations. The calculations are not simple. They require vast numerical simulations of the gravitational evolution of billions of particles representing both dark matter and ordinary matter, run on the most powerful supercomputers available. But the calculations have been done repeatedly with increasing sophistication, and they make specific predictions about what the universe should look like at different epochs. At a redshift of 10, corresponding to a time approximately 480 million years after the Big Bang, the predictions say the universe should contain small, faint, primitive galaxies. The most massive galaxies that should exist at this epoch should contain perhaps a few billion solar masses of stars. Finding galaxies with tens or hundreds of billions of solar masses of stars at this epoch would be a serious problem for the model. It would mean that something is either wrong with our understanding of how quickly galaxies can form, or wrong with our understanding of the initial conditions, or wrong with some more fundamental aspect of the cosmological framework. Before Webb, our observational data on galaxies at these extreme redshifts was limited. Hubble could detect them, but could not characterize them in detail. The galaxies at redshift 6 and above were faint, small, few in number in Hubble's images, and difficult to analyze with the precision needed to measure their stellar masses and star formation histories accurately. The Hubble data was roughly consistent with the predictions, though some tension existed even before Webb. Webb changed the situation fundamentally. Its infrared sensitivity, combined with its larger mirror and more advanced detectors, allows it to detect and characterize galaxies at redshifts that were previously inaccessible. And in its first year of science operations, it found galaxies at extreme redshifts that were significantly more massive, significantly more numerous, and significantly more evolved than the predictions allowed. Let us go through specific examples, because specific numbers are more honest than general statements about things being surprising. The galaxy catalogued as CEERS-1019 was identified in Webb's early data at a redshift of approximately 8.7, corresponding to a time about 570 million years after the Big Bang. It was already producing stars at a rate comparable to the Milky Way today. At 570 million years after the Big Bang, the Milky Way should have been a primitive proto-galactic structure. CEERS-1019 appeared to be an already substantial galaxy, with ongoing star formation at a rate implying it had been forming stars for a significant fraction of the universe's age at that point. The galaxy called GS-9209, identified at a redshift of approximately 4.66, corresponding to about 1.3 billion years after the Big Bang, was particularly striking. It contained approximately 40 billion solar masses of stars. It had already stopped forming stars. It was what astronomers call quenched, its star formation having ceased some time before it was observed. This means that within the first roughly 600 million years of the universe's existence, GS-9209 had already formed tens of billions of stars and then shut down its star formation. The models predict that such a massive quenched galaxy should not exist at this epoch. The mass alone is challenging. The quenching is especially so because quenching requires specific physical processes operating on timescales that are difficult to accommodate within the available time. The most dramatic findings came from the first analysis of Webb's deep field images, images of small patches of sky accumulated over many hours of telescope time to detect the faintest and most distant galaxies. In 2022 and 2023, multiple teams analyzing Webb deep field data reported a population of candidate galaxies at redshifts of 10, 11, 12, and even beyond, corresponding to the universe's first few hundred million years. Several of these candidates appeared to have stellar masses of billions to tens of billions of solar masses. If confirmed, these objects would be among the most challenging to explain within the standard model. The phrase "if confirmed" is important. Some of these extreme high redshift candidates are photometric redshifts, estimates of distance based on the colours of the galaxy in different wavelength bands, rather than on spectroscopic measurements of specific absorption or emission lines. Photometric redshifts are less reliable than spectroscopic ones, and some of the most extreme candidates may turn out, when spectroscopically confirmed, to be at lower redshifts where their masses are less surprising. This is a normal part of the scientific process. Photometric candidates require spectroscopic confirmation, and some fraction will not be confirmed at their estimated redshifts. But spectroscopic confirmation has been obtained for a significant number of these objects. The number of confirmed massive early galaxies is large enough and their properties anomalous enough that the tension with the standard model is real and is taken seriously by the cosmological community. It is not a case of a few extreme outliers that could be statistical fluctuations. It is a population of objects whose abundance and properties systematically exceed the model predictions. What are the possible explanations? Let us go through them carefully, because the explanations range from mundane to revolutionary, and understanding where on that spectrum the truth lies requires understanding each option clearly. The most conservative explanation is that our models of galaxy formation are wrong in detail rather than in their fundamental framework. Lambda CDM describes the gravitational evolution of dark matter with great precision. Dark matter halos form and merge on well-understood timescales. But the conversion of dark matter halo mass into stars, the process of galaxy formation within those halos, involves complex physics that is not calculated from first principles, but modelled with approximations. Gas dynamics, star formation efficiency, feedback from supernovae and supermassive black holes that can heat or expel gas and regulate star formation, all of these are incorporated into galaxy formation simulations as subgrid models, meaning they are represented by phenomenological prescriptions tuned to reproduce observed properties rather than calculated from fundamental physics. If early galaxies form stars more efficiently than current subgrid models assume, if the conversion of gas to stars in the early universe is faster and more complete than the models predict, then more massive galaxies can exist at earlier times without violating any fundamental physics. This is not a modification of the cosmological framework. It is a revision of the galaxy formation physics within that framework, and it is testable. Different assumptions about early star formation efficiency make different predictions about other observable properties of early galaxies, such as their chemical compositions and their spatial distributions. Several theoretical groups have already proposed modifications to the star formation efficiency in early galaxies that can reproduce the observed Webb galaxy counts without modifying lambda CDM. Whether these modifications are physically justified, whether there is a good reason why early star formation should be more efficient, is actively debated. The mechanisms proposed include a top-heavy initial mass function for early stars, meaning the first stars preferentially form with larger masses and burn brighter and faster, and reduced feedback from the first generation of supernovae due to the metallicity-dependent properties of stellar winds. These are plausible mechanisms. They are not entirely ad hoc. There are physical reasons to expect the initial mass function and the feedback properties to be different in the metal-poor environments of very early galaxies. But they represent modifications to models that were tuned to reproduce the properties of galaxies in the nearby universe and are now being extended to regimes where they have never been tested. The Webb observations are providing the first real test of whether these extensions are adequate. The second category of explanation is more significant. modifications to the initial conditions of structure formation. The density fluctuations in the early universe that seeded all subsequent structure were quantum fluctuations in the inflationary period, stretched to cosmic scales by exponential expansion. Their amplitude is measured by a parameter called sigma-8, and their scale dependence by the spectral index NS. If the amplitude of fluctuations on galaxy scales is larger than the standard model assumes, if sigma-8 is higher than measured, then dark matter halos form earlier and more massive galaxies can exist earlier. However, the constraints on sigma-8 from the cosmic microwave background are very tight. The CMB measurements from the Planck satellite have pinned down sigma-8 and NS to better than 1% precision. Any modification to the initial conditions large enough to explain the Webb galaxy anomaly would need to be consistent with the Planck CMB measurements, which severely constrains how much you can change sigma-8. There is an interesting wrinkle here. For several years before Webb launched, there had been a persistent tension in cosmology between the value of sigma-8 measured from the CMB, which constrains the early universe, and the value inferred from weak gravitational lensing surveys of the nearby universe. The lensing surveys consistently found a somewhat lower sigma-8 than the CMB predicts. This is called the S8 tension, and it is one of several tensions in the lambda CDM framework that were recognized before Webb added the early galaxy anomaly to the list. If sigma-8 is actually higher than lensing surveys suggest, and more consistent with the CMB predictions, if the lensing measurements have some systematic error, then the predictions for early galaxy formation might be somewhat more favorable to the Webb observations. But the discrepancy between the CMB predictions and what Webb is finding is larger than can be resolved by adjusting sigma-8 within the range allowed by existing constraints. This is not the primary explanation. The third category of explanation is more radical. Several cosmologists have suggested that the Webb early galaxy problem may require a modification to the fundamental cosmological framework, rather than just to the galaxy formation physics within it. These modifications range from modest adjustments, such as a running spectral index that allows more small-scale power in the primordial fluctuation spectrum, to more dramatic proposals involving dark matter physics. Standard cold dark matter consists of particles that were moving slowly at the time of decoupling, hence cold, and that interact only gravitationally and possibly through the weak nuclear force. Several alternatives have been proposed. Warm dark matter, particles that were moving faster at decoupling, would suppress structure formation on small scales relative to CDM. This makes the early galaxy problem worse rather than better. But self-interacting dark matter, particles that can scatter off each other, not just off ordinary matter, could, in principle, affect the internal structure of dark matter halos in ways that change the efficiency of galaxy formation. Whether self-interacting dark matter actually helps with the early galaxy problem is not yet established. A more exotic possibility is primordial black holes. If a significant fraction of dark matter consists of black holes formed in the early universe, during the inflationary period or shortly afterward, rather than particle dark matter, then the gravitational dynamics of early structure formation could be different from the standard cold dark matter case. Primordial black holes have been proposed and constrained for decades, and the constraints from various observations significantly limit the mass range and fraction of dark matter they can represent. But the parameter space is not entirely ruled out, and some versions of primordial black hole dark matter might produce enhanced early structure formation consistent with the Webb observations. There is another class of explanation that deserves special attention because it is both more concrete and more unsettling. Some of the massive early galaxies found by Webb may contain, or may be dominated by, active galactic nuclei, supermassive black holes actively accreting material and producing enormous amounts of radiation. The luminosity from an AGN can mimic or exceed the stellar luminosity of the galaxy hosting it, and if an AGN is mistakenly identified as stellar emission, the inferred stellar mass of the galaxy will be overestimated. This is a real effect. Several of the most massive early galaxy candidates found by Webb have been subsequently analysed and found to show evidence for AGN contribution to their light. If the AGN contribution is significant, the stellar mass inferred from the galaxy's brightness may be much lower than initially estimated, and the tension with the models less severe. However, this explanation does not work for all the objects in the problematic population. Some of the massive early galaxies show spectroscopic and photometric properties inconsistent with significant AGN contamination. The star-forming rates are measured through specific emission lines that trace ionized gas rather than AGN emission. The overall population excess, the fact that there are more massive early galaxies than predicted, not just one or two extreme outliers, persists even after accounting for plausible AGN contamination in individual objects. The most careful recent analyses of the Webb early galaxy population suggest that the tension with standard lambda CDM predictions is real, not an artifact of photometric redshift errors or AGN contamination, but may be somewhat less severe than the most dramatic early reports suggested. The excess is real. The galaxies are more massive and more numerous at early times than the models predict. But the discrepancy may be at the level of a factor of 2 to 10 rather than orders of magnitude, which changes the range of explanations that need to be invoked. A factor of 10 discrepancy between prediction and observation is still a major problem for any scientific model. It is not a catastrophic breakdown requiring the abandonment of everything. It is the kind of discrepancy that typically indicates something important is being missed in the models, either in the physics of galaxy formation within the standard framework, or in some aspect of the framework itself, and that resolving the discrepancy will require either better models of the known physics or new physics. Let us talk about what else Webb has found that does not fit the expectations, because the early galaxy problem is not the only anomaly emerging from Webb's observations. There are several other findings that are creating tensions with the standard cosmological model or with existing models of specific astrophysical processes. The Hubble tension is not a Webb discovery. It predates the telescope's launch by years, but Webb has contributed important new measurements that bear on it. The Hubble tension refers to the discrepancy between two different ways of measuring the current expansion rate of the universe, the Hubble constant, h0. Measurements of the Hubble constant using the cosmic microwave background, looking at the early universe and extrapolating forward to the present using the standard model, give a value of approximately 67 kilometers per second per megaparsec. Measurements using nearby distance indicators, primarily Cepheid variable stars and Type 1a supernovae, give a value of approximately 73 kilometers per second per megaparsec. These two numbers should be the same if the standard model is correct. They differ by about 9%, which is more than 5 standard deviations, well beyond what statisticians consider to be a coincidence. Webb has addressed the Hubble tension directly through its ability to measure Cepheid variables and other distance indicators with greater precision than Hubble. The initial hope was that Webb's superior resolution might reveal systematic errors in the Cepheid measurements, perhaps crowding effects in the dense stellar environments where Cepheids are found, which could cause nearby stars to artificially brighten the Cepheid measurements and bias the inferred distances. If such crowding effects were responsible for the tension, Webb would find different values for the Cepheid distances than Hubble did. Webb measured the same Cepheids as Hubble in several calibrating galaxies. The result was that Webb found essentially the same Cepheid distances as Hubble. The crowding effects that might have been responsible for a systematic bias were not significant. The local Hubble constant, measured through the distance ladder, is not an artifact of Hubble's spatial resolution limitations. The tension is real. The two measurements genuinely disagree, and the disagreement does not appear to be due to systematic errors in either measurement. This is the most important pre-Webb tension in cosmology, and Webb has confirmed rather than resolved it. The Hubble tension now sits as a genuine, unresolved discrepancy between different measurements that in the standard model should agree. Its resolution likely requires either new physics, something that affects the expansion history of the universe in a way that the standard model does not account for, or a systematic error somewhere in the distance ladder that has not been identified, despite extensive efforts to find it. Several new physics explanations for the Hubble tension have been proposed. Early dark energy, a component of dark energy that was more significant in the early universe than in the late universe, can in principle raise the early universe estimate of the Hubble constant into agreement with the local measurements. But the specific form of early dark energy needed to resolve the Hubble tension makes predictions about the CMB that are partially in tension with the Planck measurements. Different proposed solutions have different trade-offs between resolving the Hubble tension and maintaining consistency with other observations. The sigma-8 tension, mentioned earlier in the context of early galaxy formation, is related but distinct. The CMB inferred value of sigma-8 is consistent with the early galaxy numbers found by Webb being anomalously high. But the lensing surveys finding a low sigma-8 are telling us that structure in the nearby universe is less developed than the CMB predicts, which is the opposite direction from what the Webb early galaxy findings suggest. These tensions do not all point in the same direction, and they do not all have a single, simple resolution. What is emerging from this collection of tensions, the Hubble tension, the sigma-8 tension, the early galaxy problem, and several other smaller discrepancies, is a picture in which the standard cosmological model fits the data extraordinarily well overall, but shows systematic signs of stress at specific points. The model is not broken in the sense of being obviously wrong. It is stressed in the sense of having multiple independent datasets pointing to small but significant inconsistencies with its predictions. This pattern, a very successful model showing consistent but modest tension with precision data at multiple independent points, is historically a pattern that has preceded significant advances in fundamental physics. It was this pattern in classical mechanics at the end of the 19th century, the ultraviolet catastrophe, the photoelectric effect, the anomalous precession of Mercury, that pointed toward the quantum revolution and general relativity. Those anomalies were each individually small. Together, they were signals that something fundamental was missing from the theoretical framework. The resolutions required entirely new conceptual structures. The current tensions in cosmology are each individually modest. The Hubble tension is 9%, large for a precision measurement, but not obviously catastrophic. The sigma-8 tension is smaller. The early galaxy problem is a factor of a few at most after the most careful analysis. None of these individually demands new fundamental physics. But together, taken as a pattern, they suggest something may be missing from, or wrong with, the standard model in a way that more data and more careful analysis will eventually make clear. The specific nature of what might be wrong is genuinely unknown. This is not false modesty. Cosmologists have proposed dozens of modifications to the Standard Model aimed at resolving one or more of the tensions, and none has emerged as clearly superior to the others. The situation is one of genuine scientific uncertainty. There are multiple viable hypotheses, insufficient data to definitively choose between them, and active research programs aimed at obtaining the data that could make the discriminating observations. Webb is the most important of those research programs. It is producing data on the early universe at a level of detail and sensitivity that has never been available before. The early galaxy problem it has revealed may be just the beginning of a catalogue of anomalies that together will point more clearly toward whatever new physics is needed. Let us talk about what John Mather specifically said and what he meant by it, because the Nobel laureate's words deserve more context than headlines provide. Mather's statement that it is a different universe than we thought was made in the context of discussing the early galaxy findings. He was not claiming that the Big Bang didn't happen, or that the Standard Model is fundamentally broken. He was expressing the genuine scientific surprise of finding objects at early cosmic times that exceed the predictions of carefully constructed models. The phrase different universe in this context means different from what the models predicted, which is a statement about the models rather than about the physical universe itself. But it is worth understanding what Mather's surprise means, coming from someone who contributed so centrally to the observational foundation of the Standard Model. Mather received the Nobel Prize for measurements of the cosmic microwave background that confirmed the Big Bang with extraordinary precision. He then spent decades as a senior scientist at NASA and as a principal investigator of the James Webb Space Telescope. He understands the Standard Model from the inside. He knows what it predicts and why those predictions have been trusted and to what degree they can be modified before they break. When someone with that background expresses genuine surprise at observational results, the surprise is calibrated. It is not the surprise of someone encountering something they never thought about before. It is the surprise of someone who has spent decades thinking carefully about precisely these questions, and who is now looking at data that does not fit the expectations those decades of thinking generated. The phrase, "break everything we know," deserves careful interpretation. Mather was not predicting that the Standard Model will be overturned. He was expressing the possibility, which he was careful to frame as a possibility rather than a certainty, that the tensions revealed by Webb could be signals of something genuinely new in fundamental physics, rather than gaps in our models of galaxy formation. He is one of many cosmologists who holds this possibility open while working carefully to understand whether the anomalies can be explained within the existing framework. This is what good science looks like at a frontier. Not certainty in either direction, not the claim that everything is overturned, not the dismissal that nothing is really wrong. The careful acknowledgement that something unexpected is being found, that multiple explanations are possible, that the data needed to discriminate between them is being obtained, and that the outcome is genuinely uncertain. What makes Webb's findings particularly significant, beyond the specific anomalies already discussed, is the systematic nature of the information it is providing. Previous telescopes gave us glimpses of the early universe. Webb is providing a census. It is not finding one or two anomalous objects and asking whether they are real. It is finding populations of objects and asking whether the population statistics are consistent with the models. Population statistics are much harder to dismiss as statistical flukes or measurement errors than individual extreme objects. The statistical analysis of Webb's early galaxy populations is ongoing. Different teams are using different methods, different photometric redshift codes, different stellar population synthesis models, different assumptions about star formation histories, and getting somewhat different numbers for the severity of the tension. This is normal and healthy scientific practice. The results are converging on a consensus that the tension is real, but its severity is at the lower end of the initial reports. The confirmation program, obtaining spectroscopic redshifts and detailed characterizations of the most anomalous objects, is also ongoing. This work is time-consuming because spectroscopy requires longer integration times than imaging, and Webb's time is in high demand from many different science programs. But the spectroscopic data that has been obtained for a subset of the most extreme candidates has generally confirmed their approximate photometric redshift estimates and their general properties, lending credibility to the statistical anomaly as a whole. The deeper question, what the anomaly means, will take years to answer. The history of cosmology includes multiple examples of observational tensions that were resolved through better modelling of conventional physics rather than new fundamental physics, and multiple examples of tensions that eventually required genuinely new physics to resolve. The early galaxy problem could be either. At the current state of the evidence, it is not possible to say which. What is possible to say is that the James Webb Space Telescope is doing exactly what it was designed to do, pushing the boundaries of the observable universe to a new frontier and finding things that were not predicted by the models developed from previous observations. The fact that some of what it finds creates tension with those models is not a failure of the telescope or of the models. It is science working as it should. New instruments accessing new regimes, discovering new phenomena, creating new puzzles that drive new understanding. John Mather built a telescope to see things no human had seen before. The telescope is seeing them. Some of what it sees was expected, some of it was not. The things that were not expected are the most interesting things, because they are pointing somewhere that the existing map does not go. Where exactly they are pointing and how far the map will need to be redrawn to accommodate them is what the cosmological community is now working to find out. That work is happening right now. At observatories around the world and in space, scientists are collecting data on early galaxies, measuring their properties, testing them against models, building better models, designing new observations to test those models. The early universe is no longer an inaccessible frontier, visible only in blurry glimpses. It is a landscape that Webb is mapping in detail, and the features of that landscape are being compared against the predictions of the best theory we have. And where they differ, in ways that are real and significant, the theory will need to be revised. What it will be revised to is unknown. That is the honest answer. There is no leading candidate theory waiting in the wings that resolves all the tensions while preserving all the successes of the standard model. The resolution may be a modest modification to galaxy formation physics. It may be a significant modification to the cosmological framework. It may require new physics that we do not currently have any observational handle on. The data is not yet sufficient to determine which. This is the actual state of cosmology at the frontier. Precise, powerful, genuinely uncertain. A model that has worked extraordinarily well, being tested by instruments of unprecedented capability and showing signs of stress that cannot yet be definitively interpreted. Scientists of the highest caliber expressing genuine surprise at what they are finding. Questions being asked that have not been asked before because the data to ask them has not been available before. This is what it looks like when a field is at the edge of something new, not chaos, not the overthrow of everything. The specific, careful, quantitative discovery that some things are not where the map says they should be, and the beginning of the process of making a better map. The universe Webb is finding may be different from the universe the models predicted. How different, and different in what specific ways, is the question that the coming years of Webb observations and theoretical work will answer. Let us talk about the specific physics of why massive early galaxies are so difficult to explain. Because the intuitive version of the problem is that things form too quickly, and the detailed version is considerably more interesting and considerably more constrained. The formation of a galaxy requires several things to happen in sequence. First, a dark matter halo must collapse. This happens on timescales determined by the density of the universe and the amplitude of the initial density fluctuations, timescales that are calculable from the physics of gravitational collapse and that the Standard Model predicts with precision. Second, gas must fall into the dark matter halo and cool sufficiently to fragment into clouds dense enough to form stars. Gas cooling is governed by atomic physics, the rates at which hydrogen and helium can radiate away energy at different temperatures and densities, and is well understood. Third, the gas clouds must actually form stars, a process that involves complex physics, including turbulence, magnetic fields, radiation pressure, and the heating effects of newly formed stars on surrounding gas. Fourth, some fraction of the stars must live and die on timescales short enough that their supernovae and stellar winds process the gas and potentially shut down further star formation. Each of these steps takes time. The dark matter halo collapse time for halos of the mass needed to host the massive early galaxies Webb is finding is calculable, and it is comparable to, or longer than, the time available between the Big Bang and the epoch at which these galaxies are observed. This is the core of the problem. Not just that stars formed quickly, but that the entire sequence, halo collapse, gas infall, gas cooling, star formation, and in some cases quenching, had to complete within a time budget that the models say is insufficient. There are specific bottlenecks. Gas cooling is one of them. Gas falling into a dark matter halo for the first time is shock heated to the virial temperature of the halo, the temperature at which the thermal pressure supports the gas against further collapse. For massive halos, this temperature is millions of Kelvin. Gas at millions of Kelvin cools primarily through Bremsstrahlung, the radiation produced by free electrons decelerating near ions, and this process is relatively slow. The cooling time for hot gas in a massive halo can be comparable to the Hubble time, the current age of the universe, which means that in massive halos, gas simply cannot cool fast enough to form stars at high efficiency. This was recognized decades ago as a fundamental challenge for galaxy formation and led to the development of the cold streams model, the idea that in the early universe, cold, dense filaments of gas from the cosmic web could penetrate directly into dark matter halos without being shock heated, delivering cold gas to the central regions where it could efficiently form stars. Cold streams are a well-established theoretical concept, and numerical simulations have confirmed that they occur in early massive halos. They may be part of the explanation for why early galaxies formed rapidly, but whether they are efficient enough to produce the stellar masses Webb is finding in the time available is uncertain. The simulations do not clearly reproduce the observed numbers. Quenching, the cessation of star formation, is another bottleneck. Among the massive early galaxies found by Webb, a significant fraction appear to be already quenched. They have old stellar populations, meaning star formation stopped some time before they were observed. In nearby galaxies, quenching is associated primarily with feedback from supermassive black holes, active galactic nuclei that release enormous amounts of energy as they accrete material, heating or expelling the surrounding gas and shutting off the fuel supply for further star formation. This is called AGN feedback, and it is incorporated into galaxy formation models as a key regulatory mechanism. For AGN feedback to quench a galaxy, you need a supermassive black hole that has grown to sufficient mass and is actively accreting. Growing a supermassive black hole takes time. The seed black holes from which supermassive black holes grow are thought to be either remnants of the first generation of massive stars, population 3 stars, or possibly the direct collapse black holes formed from the collapse of massive primordial gas clouds without going through normal stellar evolution. Regardless of the seed mechanism, growing a black hole from a few hundred solar masses to the tens or hundreds of millions of solar masses needed to drive significant AGN feedback requires sustained accretion at high rates over millions of years. Webb is finding evidence of massive black holes at extremely high redshifts. The galaxy GN-Z11, observed at a redshift of approximately 10.6, corresponding to about 430 million years after the Big Bang, shows spectroscopic evidence for both a massive stellar population and the presence of an active supermassive black hole. The coexistence of a massive galaxy and a massive black hole at such an early epoch is itself surprising. It means that both the galaxy and its central black hole had to form and grow on timescales that the models struggle to accommodate. The discovery of massive black holes in the early universe is itself one of the most significant findings of Webb beyond the galaxy formation problem. Quasars, active supermassive black holes bright enough to be detected at extreme distances, were known before Webb to exist at redshifts above 6, corresponding to less than 1 billion years after the Big Bang. These quasars host black holes with masses of billions of solar masses. How such massive black holes could form in less than 1 billion years was already an unsolved problem. Webb is finding black holes at even higher redshifts and in galaxies that are not as luminous as quasars. Black holes that are growing but not yet at the extreme luminosities of the highest redshift quasars. The existence of massive black holes in the early universe constrains the seeding mechanism and the accretion history. If black holes start from stellar mass seeds of a few hundred solar masses and grow by accreting at the Eddington limit, the maximum accretion rate where radiation pressure from the accreted material balances gravity, they can double their mass in approximately 40 million years. From a seed of 100 solar masses to 1 billion solar masses in less than 500 million years requires sustained Eddington-limited accretion for the entire available time with no interruptions. This is extremely demanding. Real accreting black holes are not continuously at the Eddington limit. They cycle between high and low accretion states. They are sometimes obscured or starved of gas. They experience merger events that can disrupt accretion temporarily. Alternative seeding mechanisms, direct collapse black holes forming with initial masses of thousands to hundreds of thousands of solar masses, relax the accretion constraint somewhat because you start closer to the required final mass. But direct collapse black holes require specific environmental conditions: pristine gas without molecular cooling, strong ultraviolet backgrounds, that may be rare in the early universe. Whether enough direct collapse black holes form to explain the observed population of massive early black holes is an open question. Super-Eddington accretion, accretion at rates exceeding the Eddington limit through specific physical mechanisms involving radiation trapping in the accretion flow, has been proposed as a way to grow black holes faster than the standard Eddington-limited scenario. Some theoretical and simulation work suggests that episodic super-Eddington accretion is possible and could significantly accelerate black hole growth in the early universe. Whether this mechanism is efficient enough and common enough to explain the observations is actively debated. Let us now talk about something that Webb has found that is genuinely unexpected in a different way. Not just massive early galaxies, but galaxies with morphologies and structures that were not expected to exist in the early universe. The standard model of galaxy formation predicts that the earliest galaxies should be irregular, clumpy, and disorganized, the products of chaotic hierarchical merging and accretion that has not had time to produce organized structures like the spiral arms and elliptical shapes familiar in nearby galaxies. Disk galaxies, galaxies with thin rotating stellar disks like the Milky Way, require specific conditions to form. The disk must not be disrupted by major mergers. The angular momentum of the accreted gas must be organized rather than randomly oriented. The star formation must be quiescent rather than violent. All of these conditions are harder to meet in the chaotic early universe, where merger rates are higher and the gas flows are more disturbed. Webb has found disk galaxies at redshifts where they should not exist. A study published in 2023 analysed the morphologies of galaxies in Webb's deep field images at redshifts between 2 and 8, covering roughly the first 3 billion years of cosmic history, and found that thin disk galaxies are approximately 10 times more common in this early epoch than the standard model predicts. The fraction of galaxies with disk-like morphologies at high redshifts was substantially larger than expected, and some of the disks found were surprisingly thin and well organized for systems in the early universe. This is a different kind of problem from the mass excess. Disk formation is sensitive to the merger history and the angular momentum of infalling gas, processes that are implemented in cosmological simulations through specific models for how mergers randomize the angular momentum of gas and how gas accretion brings in angular momentum from the surrounding cosmic web. If disks are more common than predicted in the early universe, it suggests that either mergers are less disruptive to disk formation than the models assume, or that gas accretion is more coherent and angular momentum preserving than the models predict, or some combination of both. One proposed explanation is that in the early universe, gas accretion from cold streams was more efficient at depositing gas with coherent angular momentum, meaning the gas fell in primarily from one direction rather than randomly from all directions, which would naturally produce organized rotating disks without requiring the long dynamical relaxation times that disk formation takes in the standard model. Another is that the first generation of disk galaxies was particularly robust against merger-induced disruption because they formed in an epoch when the dark matter halos were more concentrated and the disk's self-gravity was more important relative to the perturbations from incoming satellites. These are plausible mechanisms, but they are not yet fully incorporated into the high-resolution cosmological simulations needed to test them quantitatively. The simulations that can resolve individual galaxies in detail are limited in the cosmological volume they can simulate. They cover small boxes that may not represent the full diversity of cosmic environments. The simulations that cover large cosmological volumes, large enough to have meaningful statistics on early galaxy populations, cannot resolve the internal structure of individual galaxies well enough to predict their morphologies accurately. Closing this gap requires computational resources that are still being developed. Let us talk about something specific that Webb is finding that bears on an even more fundamental question. The question of whether the universe is isotropic, meaning the same in all directions, and homogeneous, meaning the same at every location on large scales. These are called the cosmological principle, and they are foundational assumptions of the standard model of cosmology. The cosmic microwave background is almost perfectly uniform in temperature across the sky, differing by only about 1 part in 100,000 from place to place. This uniformity is the primary observational support for the cosmological principle. The universe on the larger scales looks the same in every direction, but at smaller scales, at the scale of galaxy clusters and superclusters and the cosmic web, there is structure, and the structure is not isotropic or homogeneous. Webb and large-scale galaxy surveys have been probing whether the cosmological principle holds at the scales of the structures Webb is finding. Several tentative anomalies have been reported. One of the most discussed is the finding of a large-scale asymmetry in the distribution of quasars, active galactic nuclei, that appears to persist to scales larger than structure formation models predict should be coherent. Another is the existence of some of the largest known structures in the universe, the Hercules Corona Borealis Great Wall, a concentration of galaxies spanning several billion light-years, that challenges the expectation that structure should average out to homogeneity at scales above a few 100 million light-years. These large-scale structure anomalies are less established than the early galaxy problem or the Hubble tension. The statistics are more difficult to evaluate correctly because the systematic effects in large-scale surveys are complex, and the comparison to theory requires careful treatment of survey selection effects. But they add to the growing catalogue of observations that do not fit comfortably within the standard model. The cosmological principle is important because the entire mathematical framework of the standard model, the Friedmann equations that describe the expansion of the universe, the derivation of the CMB power spectrum, the calculation of the growth rate of structure, all assume that the universe is homogeneous and isotropic on large scales. If this assumption fails, if the universe has significant structure on scales approaching the Hubble scale, the entire framework would need to be rebuilt from more general equations that do not make this simplifying assumption. This is the kind of modification that would be truly revolutionary. Not a tweak to galaxy formation models, not an adjustment to the dark energy equation of state, a revision of the foundational assumptions of the entire theoretical framework. No current evidence is strong enough to make this modification necessary. But the evidence is being collected, and the question is being asked more seriously than it was before Webb began operating. Let us now talk about what other space-based and ground-based observatories are doing to follow up on Webb's findings, because Webb does not operate in isolation. It is one node in a global network of observatories, each probing different aspects of the universe with different capabilities. The Euclid satellite, launched by the European Space Agency in 2023, is conducting a survey of billions of galaxies across a large fraction of the sky, designed to measure the distribution of galaxy shapes and positions to unprecedented precision. Its primary science goals are the measurement of dark energy through the statistics of galaxy clustering and weak gravitational lensing, and the measurement of the growth rate of cosmic structure. Euclid's data will provide a powerful test of the standard model on large scales, and will detect any large-scale structure anomalies with much greater statistical significance than current surveys. The Vera Rubin Observatory, under construction in Chile and expected to begin full science operations in the mid-2020s, will conduct the legacy survey of space and time, imaging the entire southern sky repeatedly over 10 years and detecting billions of galaxies, supernovae, variable stars and transient events. Its dataset will be the most comprehensive photometric survey of the universe ever compiled, and will provide exceptional constraints on cosmological parameters through multiple independent methods. The Square Kilometre Array, a giant radio telescope being built in South Africa and Australia, consisting of thousands of individual radio antennas combined to form an aperture equivalent to a square kilometre, will survey hydrogen gas across cosmic time, mapping the large-scale distribution of matter and the evolution of galaxies through their gas content in ways that complement optical and infrared surveys. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will conduct wide-field infrared surveys with a field of view 100 times larger than Webb's, detecting hundreds of millions of galaxies out to high redshifts. Roman is specifically designed to address cosmological questions, including dark energy and the Hubble constant, through large statistical samples of supernovae and gravitational lensing. These observatories together will provide a much more complete picture of the universe than any single telescope can provide. The tensions that Webb has identified, and that Euclid and Roman and Rubin will investigate with far larger statistical samples, will either be confirmed and sharpened or resolved and explained through better data. The next decade of observational cosmology will be one of the most data-rich in history. On the theoretical side, the challenge is equally significant. The anomalies found by Webb have motivated a substantial increase in theoretical activity. New proposals for modifications to the Standard Model, new high-resolution simulations designed to probe the early universe, new analyses of existing CMB and large-scale structure data looking for signs of the same underlying physics that might explain the Webb findings. One theoretical approach that has gained attention is early dark energy, a component of dark energy that was more significant in the first few million years of cosmic history than today. Early dark energy was proposed primarily to address the Hubble tension, but if it modified the expansion rate of the early universe, it would also affect the rate of structure formation. The specific effect depends on the equation of state and the time evolution of the early dark energy component, and different models make different predictions for early galaxy formation. Some models of early dark energy could, in principle, alleviate both the Hubble tension and the early galaxy excess simultaneously. Whether the specific form needed to do both is consistent with CMB constraints is an active area of research. Another theoretical direction is interacting dark matter, models in which dark matter particles interact with each other, or with ordinary matter, or with photons, through forces beyond gravity. Such interactions could affect the collapse of dark matter halos and the formation of the first galaxies in ways that might alleviate the early galaxy problem. The parameter space of interacting dark matter models is large, and most of it has not been fully explored in the context of early galaxy formation. String cosmology, models inspired by string theory in which the fundamental constants of nature, or the effective properties of dark energy, vary in time, has been proposed in various forms as a framework for understanding some of the tensions in the Standard Model. These models are generally more speculative than the dark energy and dark matter modifications discussed above, but are motivated by theoretical considerations about the nature of the cosmological constant problem. The question of why dark energy has the specific tiny value it has. The theoretical landscape is rich and unresolved. Many models exist, and none has emerged as clearly superior to the others. The data being collected by Webb and by the upcoming generation of surveys will impose stronger constraints that will eliminate some models and identify which, if any, of the surviving models can explain the full range of observations consistently. Let us talk about what is perhaps the most philosophically significant implication of what Webb is finding. Not the specific anomalies, but what those anomalies reveal about the nature of scientific knowledge and the relationship between theory and observation at the frontier of what is knowable. The Standard Model of cosmology is one of the most successful scientific theories in history by the measure of quantitative precision. It has made dozens of specific numerical predictions that have been confirmed by independent observations to levels of accuracy that would have seemed impossible just decades ago. The agreement between CMB measurements and the Standard Model's predictions for the pattern of temperature fluctuations is better than 1% across dozens of independent angular scale measurements. This is not luck. It reflects a deep truth about the structure of the universe captured by the model. And yet, the model is not the universe. It is a representation of the universe, a simplified mathematical description that captures the most important features, but inevitably leaves something out. Every model is wrong in some respects. The question is, which respects and how much? For half a century, the Standard Model's errors have been too small to matter for any practical observational purpose. The observations were not sensitive enough or precise enough to reveal them. Webb is sensitive enough, precise enough. It is looking at the universe in a regime, the very early universe, where the model's predictions have never been tested with this level of detail. And it is finding that the models are wrong, at least in their predictions for early galaxy formation, by amounts that are not negligible. This is how science makes progress at frontiers, not by finding that everything is exactly as predicted, by finding where the predictions fail and using those failures to understand what the predictions are missing. The failures of the Standard Model in the early universe, if they are confirmed as more data is collected and analysed, are pointing at something that the model does not capture. Something about how galaxies form, or about the initial conditions of the universe, or about the nature of dark matter or dark energy that is different from what the model assumes. What that something is, precisely what new understanding is needed to reconcile the Webb observations with the cosmological framework, is not yet known. This is the honest statement, not that everything is broken. Not that the Standard Model is wrong in some fundamental, catastrophic way, but that something is missing, that the missing thing is being pointed at by specific observational anomalies, and that finding the missing thing will require both more observations and new theoretical ideas that do not yet exist in fully developed form. John Mather's statement that it is a different universe than we thought captures this situation better than either of the extreme interpretations that headlines typically offer. He is not saying the universe is fundamentally incomprehensible or that cosmology has failed. He is saying that the universe is more complex, more surprising, and richer in physical phenomena than the models built before this level of observational access had achieved told us it would be. This is good news for science. Surprising observations are the engine of scientific progress. They are what demand new ideas and drive new understanding. Webb is delivering surprising observations at a rate and depth that the scientific community is still processing. the early galaxy problem is the most discussed, but not the only anomaly. The disk galaxy fraction, the black hole mass function at high redshift, the quenching timescales, the spatial distribution of early massive galaxies, all of these are being measured with precision for the first time, and all of them are providing data that the theoretical framework must now account for. The cosmological community is responding with exactly the kind of serious engagement that frontier anomalies deserve. New simulations are being run, new theoretical models are being developed, new observational programs are being designed to test specific predictions of specific alternative models. The science is working as science should work, following the evidence, taking the anomalies seriously, building new understanding from the places where the old understanding fails. What the new understanding will look like, whether it is a modest revision to galaxy formation physics or a significant modification to the cosmological framework, or something more fundamental that requires new conceptual structures, is genuinely unknown. The data will tell us. Webb will be a central part of that conversation for the next decade, and the universe it is finding, richer, earlier formed, more structured and organized in its infancy than the models predicted, is not a universe that is breaking our understanding. It is a universe that is challenging our understanding, pushing it further, demanding that it become more precise and more complete. This is what telescopes are for, not to confirm what we already know. To show us what we did not know, let us talk about the specific technical capabilities of James Webb that allow it to see what Hubble could not. Because the physics of why Webb can detect galaxies 13 billion light-years away that Hubble missed is directly relevant to understanding why the anomalies it is finding are real and not artifacts of improved instrumentation. The most fundamental difference between Webb and Hubble is the wavelength range each telescope observes. Hubble primarily works in ultraviolet and visible light, wavelengths from about 0.1 to 1.7 micrometers, with its sensitivity concentrated in the range visible to the human eye. Webb works primarily in the near and mid-infrared, from about 0.6 to 28 micrometers, with peak sensitivity in wavelengths that no previous space telescope could access with comparable efficiency. This difference is critical for studying the early universe because of a phenomenon called cosmological redshift. As the universe expands, light travelling through it has its wavelength stretched by the same factor by which the universe has expanded since the light was emitted. A galaxy at redshift 10, a galaxy whose light has been travelling for about 13.3 billion years, has had its light stretched by a factor of 11. Light that was emitted as ultraviolet is now arriving as near-infrared. Light emitted as visible is now arriving as far-infrared. The entire spectral energy distribution of the galaxy has been shifted dramatically to longer wavelengths. This means that studying a galaxy at redshift 10 requires an infrared telescope. Hubble simply cannot detect the light from these galaxies efficiently because that light is now at wavelengths where Hubble has no sensitivity. Webb was specifically designed to access the infrared wavelengths where the light from the very early universe arrives after billions of years of cosmological redshifting. Its infrared capability is not incidental. It is the entire scientific rationale for building it in the first place. Webb's mirror is also substantially larger than Hubble's. Hubble's primary mirror is 2.4 meters in diameter. Webb's is 6.5 meters, about 2.7 times larger in diameter, which means about 7.4 times more collecting area. More collecting area means fainter objects can be detected. For the most distant galaxies, objects that are genuinely faint partly because they are far away and partly because they were genuinely less luminous than nearby galaxies, this difference in collecting area is crucial. Webb can detect objects that Hubble would need impossibly long exposure times to observe at all. Webb's infrared detectors are also more sensitive than Hubble's near-infrared instruments because they operate at temperatures closer to absolute zero. The MIRI instrument operates at -266 degrees Celsius, colder than any naturally occurring environment in the solar system. At these temperatures, the thermal noise generated by the detectors themselves is negligible, allowing extremely faint astronomical signals to be detected against a quiet background. This is why the sun shield, the 5-layer thermal barrier that keeps Webb cold, is not just an engineering convenience, but a scientific requirement. The combination of larger mirror, infrared sensitivity, and cold detectors makes Webb approximately 100 times more sensitive than Hubble for infrared observations of faint, distant objects. This is not a modest improvement, it is a transformation of capability. The difference between seeing a candle at a kilometre and seeing it at 10 kilometres. But sensitivity alone would not produce the science Webb is producing. Resolution matters too, the ability to distinguish fine spatial detail in the images. At the wavelengths Webb observes, its angular resolution is comparable to Hubble's at visible wavelengths, approximately 0.1 arcseconds for near-infrared observations with NIR-CAM. This is sufficient to resolve the morphologies of distant galaxies, to see whether they are disks or ellipticals, whether they have clumpy or smooth distributions of stars, whether they show signs of recent mergers or ongoing interactions. The combination of sensitivity and resolution is what allows Webb to not just detect early galaxies, but to characterize them in the detail needed to compare with model predictions. The infrared spectroscopic capabilities of Webb are equally important. NIR-SPEC, the near-infrared spectrograph, can obtain spectra of up to 100 objects simultaneously using a micro-shutter array, a grid of 250,000 individually controllable tiny shutters that can be opened to admit light from specific target galaxies while blocking everything else. This multiplexing capability means that Webb can conduct spectroscopic surveys of early galaxies efficiently. Rather than spending long periods on single objects, it can characterize many objects at once. Spectroscopic redshifts measured from the positions of specific atomic lines in galaxy spectra, are far more reliable than photometric estimates and are essential for confirming that the distant galaxy candidates are at the extreme distances the photometric estimates suggest. The first spectroscopic surveys of Webb's early galaxy candidates have been transformative. Systematic programs like JADES, the JWST Advanced Deep Extragalactic Survey, have obtained spectroscopic redshifts for hundreds of galaxies in Webb's deep fields, confirming that substantial numbers of high redshift galaxies exist at the distances the photometric analyses predicted. The spectroscopic confirmation rate for high redshift candidates has been high enough to rule out the possibility that the anomalous population is dominated by foreground interlopers misclassified as high redshift objects. The spectroscopic data also provides information beyond just redshift confirmation. The specific emission and absorption lines in a galaxy's spectrum carry information about the temperature, density, and ionization state of its gas, its star formation rate, its chemical composition, and the presence of an active galactic nucleus. For the massive early galaxies that are challenging the models, This information is crucial. It allows astronomers to determine whether the inferred properties are physically self-consistent and whether alternative explanations like AGN contamination can be ruled out. One spectroscopic finding that has attracted particular attention is the detection of emission lines from extremely metal-poor gas in some early galaxies. Metal-poor gas, gas with very low abundances of elements heavier than hydrogen and helium, is a signature of very early star formation because the heavy elements are produced by stellar nucleosynthesis and supernova enrichment and only gradually accumulate in the interstellar medium as successive generations of stars form and die. Detecting metal-poor gas in the most distant galaxies is consistent with these being genuinely early objects rather than foreground galaxies at lower redshifts. The specific abundance patterns also carry information about the nature of the earliest stars, the population 3 stars that formed from pristine hydrogen and helium gas, and how their deaths enriched the surrounding medium. The detection of signatures potentially related to population 3 stars would be one of the most significant individual findings of the Webb mission. Population 3 stars, the first generation of stars formed from primordial gas with no metals, have never been directly observed. They are predicted to be very massive, very hot, and very luminous, burning through their hydrogen fuel in just a few million years before exploding as supernovae or collapsing to black holes. Their nucleosynthetic products, the specific pattern of heavy elements they produce, would differ from those of later stellar generations and could, in principle, be identified through detailed spectroscopic analysis of the most metal-poor early galaxies. Several candidate detections of population 3 star signatures have been reported from Webb spectroscopy. These reports are preliminary and contested. The evidence is subtle, and alternative interpretations involving very metal-poor but not primordial gas are possible. But the reports exist, and they are being taken seriously by the community. The detection of population 3 stars, if confirmed, would be the observation of the very first stars that ever formed in the universe. It would represent direct access to the beginning of the stellar epoch in a way that nothing before Webb made possible. Let us talk about what Webb is finding about the interiors of galaxies, about the distribution of stars and gas and black holes within individual galaxies in the early universe. Because understanding how galaxies are structured internally, in addition to how massive they are and how many there are, provides constraints on formation models that population statistics alone cannot provide. High-resolution imaging of early galaxies with Webb has revealed that many of them are compact, significantly smaller in physical size than galaxies of similar mass in the nearby universe. A galaxy with tens of billions of solar masses of stars at redshift 8 may be only a kiloparsec or a few kiloparsecs across, the physical size of just the central bulge of the Milky Way, while a galaxy of similar mass today would typically span tens of kiloparsecs. This compactness has been observed with Hubble for galaxies at intermediate redshifts and is expected in general terms. Galaxies grow in size over time through mergers and accretion of material from the surrounding cosmic web. But Webb is revealing this compactness in detail at earlier epochs and for more extreme objects than Hubble could access. The compactness of early massive galaxies has important physical implications. A galaxy that is compact has a higher central stellar density, more stars packed into a smaller volume. Higher stellar density means higher rates of stellar interactions, which could affect the formation of compact stellar remnants and binary systems. It also means a deeper gravitational potential well, which could affect how gas flows within the galaxy and how efficiently star formation proceeds. And it means that the relationship between the galaxy's stellar mass and the mass of its central black hole, the so-called M-sigma relation that is a fundamental empirical relationship in galaxy evolution, may be different in the early universe from what it is today. The M-sigma relation, the tight correlation between the mass of a supermassive black hole and the velocity dispersion of stars in the central bulge of its host galaxy, is one of the most puzzling empirical regularities in astrophysics. It implies that the formation of the central black hole and the formation of the stellar component of the galaxy are connected in some fundamental way, that the same processes that built the stars also built the black hole, or that feedback from the black hole regulated the growth of the stars. In the nearby universe, this relation holds over 5 orders of magnitude in black hole mass, with surprisingly small scatter. In the early universe, Webb is finding evidence that this relation may not hold in the same form. Several early massive galaxies appear to have black holes that are overmassive relative to their host galaxies, compared to the local M-sigma relation. The black hole is a larger fraction of the total galaxy mass than it would be in a nearby galaxy of comparable total mass. This could mean that black holes grew preferentially quickly in the early universe, growing faster than the stellar component, before the two eventually came into the synchronization reflected in the local relation. Or it could mean that the stellar component is underestimated, that not all the stars in these early galaxies are being detected because some are too faint or too embedded in dust. Dust is an important complication in the interpretation of Webb's early galaxy observations. Dust grains in interstellar space absorb ultraviolet and visible light and re-radiate it at far infrared wavelengths. In galaxies with high star formation rates, which produce large numbers of massive ultraviolet bright stars, the dust column can be substantial and can obscure large fractions of the stellar light. Webb's infrared sensitivity mitigates some of this. Infrared light penetrates dust more easily than visible light. But at the most extreme infrared wavelengths, dust emission rather than stellar emission dominates, and Webb's detectors are not optimized for this regime. Some early massive galaxies may be substantially more massive in stars than their optical and near-infrared appearance suggests, if they harbor large amounts of dust. The Atacama Large Millimeter Array, ALMA, which observes at millimeter wavelengths where dust emission peaks, has detected far infrared emission from some of the most massive early galaxies identified by Webb, confirming that significant dust is present. The stellar masses inferred from Webb data alone may therefore be underestimates, which would mean the tension with the models is even more severe than the current analyses suggest. Alternatively, better dust models applied to the Webb data might reveal that current mass estimates are already accounting for dust adequately. Resolving this requires multi-wavelength data, combining Webb and ALMA observations systematically. Let us talk about one of the most unexpected categories of Webb's early universe findings, the discovery of what appear to be extremely massive black holes at redshifts above 10, in objects that do not look like classical luminous quasars, but more like ordinary galaxies with unusually bright centers. These objects, sometimes called little red dots because of their compact appearance and red colors in Webb images, were not predicted by any pre-Webb model. They are numerous, far more numerous than the models of quasar evolution predicted should exist at these redshifts. They appear to host black holes with masses of tens of millions to hundreds of millions of solar masses, substantial masses for objects at a time when the universe was only a few 100 million years old. But they are not as luminous as classical quasars with comparable black hole masses, suggesting either that the black holes are accreting at sub-Eddington rates, or that their emission is obscured by dust. The little red dots pose a challenge to models of black hole growth that is distinct from and complementary to the early galaxy problem. If black holes of these masses exist in large numbers at redshift 10 or higher, they represent a population of massive black holes that formed very quickly from whatever seeds existed in the earliest universe. Their properties constrain the seeding mechanism and the early accretion history in ways that require detailed theoretical modeling to interpret. Several theoretical explanations have been proposed. Direct collapse black holes forming from the direct collapse of massive gas clouds without going through normal stellar evolution, could, in principle, produce seeds massive enough to grow to the observed masses in the available time. Alternatively, massive black holes could grow through a series of mergers of smaller black holes, rather than primarily through gas accretion. Gravitational wave-driven mergers can grow black hole mass without the luminosity constraints that apply to accretion. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves from merging massive black holes and will provide direct observational constraints on the merger history of black holes in the early universe. The little red dots also raise questions about the relationship between black hole growth and galaxy growth in the earliest universe. If black holes grew very rapidly while their host galaxies were still small and primitive, if the overmassive black hole fraction seen in the early universe reflects a fundamentally different growth sequence than the one that produced the local M-sigma relation, then our understanding of the co-evolution of galaxies and their central black holes needs significant revision. This is an area of active research, with new data from Webb's spectroscopic programs being analysed and compared to theoretical models on timescales of months rather than years. The pace of discovery from Webb is itself noteworthy. In its first 2 years of science operations, the telescope has produced more data relevant to the early universe than the previous generation of telescopes produced in decades. The number of peer-reviewed papers based on Webb data is growing at a rate that the community is struggling to keep pace with. New discoveries are announced regularly, not all of them as dramatic as the early galaxy problem or the little red dots, but all of them adding to the picture of what the early universe looked like and how it evolved. This pace will continue. Webb has enough cryogen to operate for 20 years based on the efficiency of its launch trajectory. The telescope is performing better than its specifications. Its optics are aligned more precisely than required. Its instruments are more stable than expected. Its pointing accuracy exceeds the design requirements. These better-than-expected performances translate directly into better science. Longer effective exposure times for a given calendar time. Better calibration of systematic effects. More precise measurements of faint galaxy properties. The next decade of Webb science will probe the early universe systematically rather than through pioneering first glimpses. Large programs covering substantial fractions of the sky at depths sufficient to detect galaxies at redshift 10 and above will provide the statistical samples needed to definitively characterize the early galaxy population and compare it quantitatively to model predictions. Spectroscopic follow-up of thousands of high redshift candidates will confirm their redshifts and characterize their physical properties. Coordinated observations with ALMA, with ground-based extremely large telescopes, with radio surveys, and eventually with Roman, will provide the multi-wavelength context needed to understand the complete picture. The theoretical community is investing heavily in new simulations designed to interpret these observations. The FIRE simulations, the illustrious TNG simulations, the EAGLE simulations, and their successors are being extended to higher redshifts and smaller physical scales, with updated prescriptions for the physical processes that govern galaxy formation. The predictions of these simulations for the population of early massive galaxies are being compared directly to Webb data, and the comparisons are driving revisions to the models in ways that the pre-Webb theoretical frameworks did not anticipate. What is emerging from this activity is a more complete picture of galaxy formation than was possible before Webb. A picture that preserves the core successes of the lambda CDM framework, while acknowledging that the physics of how galaxies form within that framework is more complex, more efficient at early times, and more diverse in its outcomes than the pre-Webb models captured. Whether this more complex picture will eventually require modifications to the cosmological framework itself, to the initial conditions, to the nature of dark matter, to the properties of dark energy, or whether it can be accommodated entirely within lambda CDM through better modelling of baryonic physics, is the central open question of the field. The answer is being determined by data, by Webb images showing galaxies that should not exist, by Webb spectra confirming that they are at the distances claimed, by ALMA detections revealing the dust and gas content of the most extreme objects, by ground-based spectrographs measuring the dynamics of stars and gas within early galaxies, by theoretical simulations testing whether any model can produce the observed populations, by Euclid and Roman and Rubin mapping the large-scale structure context within which these early galaxies formed. This is the actual frontier of cosmology, not a moment of crisis where the standard model is collapsing. A moment of challenge where the standard model is being tested at precisions and in regimes where it has never been tested before, and where those tests are revealing that the model, extraordinarily successful as it is, does not fully capture the complexity of what the universe actually did in its first billion years. John Mather's telescope is finding that the universe is different from what he thought it would be when he conceived the telescope. This is what telescopes are supposed to do, not find what we already know, find what we do not know, and then sit with the findings carefully, rigorously, with appropriate skepticism and appropriate wonder, until the new knowledge has been built that can explain them. That building is happening now, in every observatory on Earth and in space that is pointed at the early universe, in every research group analysing Webb data, in every simulation running on every supercomputer trying to reproduce what Webb has seen, in every theorist sitting with an anomalous data point trying to understand what it means. The universe Webb is finding is richer and stranger and more interesting than the models predicted. And that is not a problem for science. That is what science is for. The cosmic microwave background is the oldest light in the universe. It was emitted 380,000 years after the Big Bang, when the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, a moment called recombination. Before recombination, the universe was an opaque plasma. Photons could not travel freely because they were constantly scattering off free electrons. At recombination, the universe became transparent, and those photons began their 13.8 billion year journey through an expanding universe. We detect them today as microwave radiation coming uniformly from all directions at a temperature of 2.725 Kelvin, the cosmic microwave background. The CMB is not perfectly uniform. It has tiny temperature fluctuations of approximately 1 part in 100,000 from place to place on the sky. These fluctuations are the primordial density variations that seeded all subsequent structure. The same quantum fluctuations that became the seeds of the cosmic web, the seeds of galaxy clusters, the seeds of individual galaxies. The pattern of these fluctuations, specifically their statistical properties described by the power spectrum, encodes an enormous amount of information about the universe at the moment of recombination and through the entire history of the universe up to that point. The Planck satellite measured the CMB temperature fluctuations with exceptional precision, mapping the temperature across the full sky at angular scales from the full sky down to a few arc minutes, with sensitivity better than a few microkelvin. The resulting power spectrum contains hundreds of independent data points, each measured to better than 1% precision in some cases. Fitting the lambda CDM model to this data determines the 6 fundamental cosmological parameters of the standard model: the density of ordinary matter, the density of dark matter, the density of dark energy, the expansion rate, the amplitude and spectral index of the primordial fluctuations, with errors of a few percent or less. This is the precision that makes the Hubble tension so significant. The Planck CMB data determines the Hubble constant to approximately 0.5% precision. The local distance ladder measurements also achieve 0.5% or better precision for the best calibrated measurements. When two measurements, each precise to 0.5%, disagree by 9%, 18 times their combined uncertainty, this is not a small discrepancy that might go away with slightly better data. It is a genuine and significant tension. The CMB also provides the baseline for evaluating the early galaxy problem. The Planck data pins down sigma 8, the amplitude of matter density fluctuations on the scale of galaxy clusters, to approximately 1% precision. The predicted number of massive dark matter halos at high redshift follows directly from sigma 8 and the other CMB constrained parameters through well-established mathematical frameworks. The galaxy formation efficiency, the fraction of dark matter halo mass that converts to stars, is separately constrained by observations of nearby galaxies. When these constraints are combined, the prediction for the number of massive galaxies at redshift 8 and above follows from physics that is tightly pinned down by data that has nothing to do with high redshift galaxy observations. This is why the early galaxy problem is not trivially resolvable by saying the models were just guessing. The models are making quantitative predictions based on parameters measured with high precision from independent data. The predictions fail. The failure is significant, and resolving it requires either modifying the galaxy formation physics in specific ways that may be physically motivated, or modifying the cosmological parameters in ways that would require consistency with all the other data that constrains them. The situation is reminiscent, in structure if not in scale, of a classic episode in the history of physics. In the 1980s and 1990s, the standard model of particle physics was extraordinarily successful at predicting the results of particle physics experiments. But precision measurements of the properties of the W and Z bosons at the Large Electron-Positron Collider at CERN revealed that the standard model's predictions and the measurements agreed at the level of 1 in 1,000, and the tiny remaining discrepancies implied the existence of a new particle, the top quark, at a specific mass that was subsequently confirmed. The precision of the measurements made the small discrepancies meaningful. They were pointing at new physics that the model did not include. The cosmological situation today is different in that the discrepancies are larger than 1 in 1,000. They are percent-level tensions rather than per mille tensions, but the logic is the same. high-precision measurements of a well-tested model revealing systematic tensions that may be pointing at something the model does not capture. The history of physics suggests taking such tensions seriously rather than assuming they will disappear with more data. Let us now talk about specific alternative cosmological frameworks that have been proposed to explain some or all of the tensions, not as speculations, but as theoretical proposals with specific predictions that can be tested. Modified Newtonian dynamics was proposed by Mordechai Milgrom in 1983 as an alternative to dark matter that modifies the gravitational force law at very low accelerations. MOND has been remarkably successful at explaining the rotation curves of individual galaxies, the same observational phenomenon that first indicated the need for dark matter, without invoking any invisible matter. In MOND, the effective gravitational force at very low accelerations is stronger than Newtonian gravity predicts, which means that stars at the edges of galaxies orbit faster than they would in Newtonian gravity without dark matter, reproducing the flat rotation curves. However, MOND in its original form fails spectacularly at the scale of galaxy clusters, where dark matter is needed to explain the dynamics and gravitational lensing, even if MOND is assumed. It also has difficulty reproducing the large-scale structure of the cosmic web and the pattern of the CMB without additional physics beyond the original modification. Relativistic extensions of MOND, most notably TeVe's tensor-vector-scalar gravity, proposed by Jacob Bekenstein, exist but have their own problems, including predicting an incorrect CMB power spectrum. More recent MOND-inspired frameworks, including covariant emergent gravity and various incarnations of modified inertia, are being actively developed and tested against observations. Whether any of these alternatives can simultaneously explain the rotation curves of individual galaxies, the dynamics of galaxy clusters, the CMB power spectrum, and the early galaxy findings of Webb is not yet established. The betting among professional cosmologists remains strongly that dark matter is real, and that MOND-type modifications are not the right framework. But the fact that MOND exists and has partial successes is a reminder that the evidence for dark matter, while compelling, is all gravitational. We have never directly detected a dark matter particle, and alternative gravitational frameworks deserve continued investigation. A more radical alternative framework is the cyclic universe, a cosmological model in which the Big Bang was not the beginning of time, but a bounce from a previous contracting phase of the universe. In cyclic models, the universe oscillates between expanding and contracting phases, and the initial conditions of each Big Bang are determined by the state of the previous cycle. Paul Steinhardt and Neil Turok developed a specific cyclic cosmology called the ekpyrotic universe, in which each cycle is driven by the collision of extra-dimensional branes in string theory. Cyclic models can, in principle, produce a scale-invariant spectrum of primordial perturbations, the same kind of spectrum that inflation produces and that the CMB observations confirm, through a different mechanism than exponential inflationary expansion. They also naturally produce a universe with very low entropy at the start of each cycle, which addresses the thermodynamic puzzle of why our universe started in such a special low entropy state. Whether cyclic models can be made consistent with all the cosmological observations, and whether they make different predictions from inflationary models that could be tested observationally, is an active area of research. For the specific tensions that Webb is highlighting, the cyclic universe does not obviously provide solutions to the early galaxy problem or the Hubble tension. These tensions are about the evolution of the universe within the expanding phase we are in, not about the initial conditions. But if the initial conditions of the universe are different in a cyclic model from what inflationary models predict, the predictions for galaxy formation could in principle differ in ways that alleviate the tensions. This has not been worked out in detail. Varying fundamental constants represent another class of alternative frameworks. The fundamental constants of nature, the gravitational constant g, the speed of light c, the fine structure constant alpha, the proton to electron mass ratio, are treated as fixed in the standard model. But in some theoretical frameworks inspired by string theory and extra dimensions, these constants can vary in space and time. If the gravitational constant was different in the early universe from today, the rate of structure formation would be different, and the predictions for early galaxy masses could be modified. Observational constraints on the variation of fundamental constants are remarkably tight. Spectroscopic measurements of absorption lines in distant quasar spectra can, in principle, detect changes in the fine structure constant over cosmic time. Different atomic transition wavelengths have different dependencies on the fine structure constant, and comparing these wavelengths in distant quasar spectra to their laboratory values reveals any cosmological variation. Such measurements have found no significant variation of the fine structure constant at the level of a few parts per million over the past several billion years. Constraints on the variation of G are less direct, but also tight from various astrophysical arguments. For the early galaxy problem, the relevant question is whether the fundamental constants could have been different enough in the first billion years to substantially alter galaxy formation rates without violating the tight constraints from later epochs. This is difficult to arrange because the constraints from the CMB, which is sensitive to the values of constants at recombination 380,000 years after the Big Bang, are already very tight. A variation in G at the level needed to produce substantially more galaxy formation in the first billion years would need to revert to its current value quickly enough to be consistent with the CMB constraints, which requires a very specific and somewhat contrived time evolution. Let us now talk about something that is less often discussed in the context of the Webb anomalies, but that may be central to understanding them: the role of environment in galaxy formation, and whether the specific regions of the early universe that Webb is observing are representative of the average early universe. The early universe was not homogeneous even on scales relevant to galaxy formation. The cosmic web was already beginning to establish itself in the first billion years. Dense nodes, the precursors of galaxy clusters, were forming at the intersections of filaments. Voids, underdense regions, were already emptying. The probability of finding a massive galaxy is not uniform across the sky. Massive galaxies preferentially form in overdense environments, in the protocluster regions where dark matter halos are forming earliest, and where the conditions for rapid star formation are most favourable. Webb's deep field observations cover small patches of the sky. The volume sampled at very high redshifts is small. If any of the deep fields happens to intercept a protocluster region or an overdense filament, the number of massive early galaxies in that field will be substantially higher than the cosmic average. This is called cosmic variance, and it is a real effect that affects all surveys of small cosmic volumes. The early papers reporting massive early galaxies in Webb data discussed cosmic variance as a potential contribution to the observed excess. The question is whether cosmic variance alone, without any modification to the galaxy formation models, could explain the full observed excess. The quantitative analysis suggests that cosmic variance can account for some of the excess, but not all of it. The excess appears across multiple independent fields and is present even in the largest contiguous Webb surveys, which reduces the impact of cosmic variance but does not eliminate it entirely. Larger area surveys, surveys covering hundreds or thousands of square degrees rather than the few square degrees of Webb's deep fields, would reduce the cosmic variance uncertainty dramatically. This is one of the primary science motivations for the Roman Space Telescope, with its much wider field of view. Roman will be able to survey areas hundreds of times larger than Webb's deep fields, and will detect enough early massive galaxies to measure their statistics with cosmic variance reduced to a negligible level. The environmental context of the Webb early galaxy anomalies matters for understanding the physics too. If the most massive early galaxies are in proto-cluster environments, as would be expected from the physics of hierarchical structure formation, where the densest environments host the earliest and most massive structures, then their properties should be compared to model predictions for overdense environments, rather than the average cosmic environment. The models may predict dense environments correctly while underpredicting the average, or they may fail in overdense environments specifically. Distinguishing between these possibilities requires knowing the environments of the early massive galaxies that Webb is finding. Some of the most extreme early galaxy candidates found by Webb are in fields that show overdensities of galaxies at similar redshifts, suggestive of proto-cluster environments. This is qualitatively consistent with expectations, but needs more detailed analysis to determine whether the overdensities are as extreme as would be needed to explain the galaxy masses through environment effects alone. Spectroscopic confirmation of many galaxies in the same field, determining whether they are at the same redshift and hence genuinely clustered, is the observational program needed to address this. Let us talk about what the epoch of reionization, the period when the first stars and galaxies ionize the surrounding neutral hydrogen gas, tells us about early galaxy formation and what Webb is measuring about it. Before the first stars formed, the universe was filled with neutral hydrogen gas, the product of Big Bang nucleosynthesis that had cooled through the cosmic dark ages following recombination. This neutral hydrogen would absorb ultraviolet light with photon energies above the hydrogen ionization threshold, 13.6 electron volts. The first stars and galaxies produced ultraviolet photons that began to ionize the surrounding hydrogen. This ionization expanded outward from each source in bubbles that eventually merged and reionized the entire intergalactic medium. The process of reionization completed somewhere between redshift 6 and 8, based on multiple observational indicators, approximately 1 billion years after the Big Bang. Understanding the epoch of reionization requires knowing how many ultraviolet photons the first galaxies produced and how efficiently they escaped into the intergalactic medium. The production rate depends on the star formation rate and the initial mass function of the early stars. The escape fraction, the fraction of ionizing photons that actually escape rather than being absorbed within the host galaxy, depends on the geometry and density of the gas in and around early galaxies. Webb is measuring the properties of galaxies during and before the epoch of reionization with unprecedented detail. The star formation rates, the stellar populations, and most importantly, the ionizing photon production efficiencies of early galaxies can be measured from their spectra. The escape fractions are harder to measure directly because ionizing photons at wavelengths below the hydrogen-Lyman limit are absorbed by the intergalactic medium before reaching us. But they can be inferred from the detailed morphology and kinematics of the galaxies and from the properties of their surrounding gas. What Webb is finding about the epoch of reionization is itself surprising. The galaxies at the right epoch to be responsible for reionization appear to be producing more ionizing photons than pre-Webb models predicted they should. Combined with the finding that there are more massive galaxies than expected at these redshifts, this suggests that the early universe was a more efficient producer of ionizing photons than the models assumed. This is consistent with the overall picture that star formation in the early universe was more efficient than models predicted. More stars forming faster from available gas, with the resulting photons contributing more effectively to reionization. This consistency between the early galaxy excess and the reionization photon budget is scientifically significant. It suggests that whatever modification to the standard galaxy formation models is needed to explain the early galaxy masses may also naturally explain the efficiency of reionization. The two anomalies may have a common cause, a common modification to the star formation efficiency or feedback physics in early galaxies, rather than requiring two separate explanations. The epoch of reionization is also being probed by 21 centimeter radio observations. The neutral hydrogen that existed before and during reionization emits radio waves at a rest wavelength of 21 centimeters, the hyperfine transition of neutral hydrogen. Observations of this emission or absorption against the radio background can, in principle, trace the three-dimensional distribution of neutral hydrogen during reionization and map the growth of the ionized bubbles. This requires observations at very long radio wavelengths, where the 21 centimeter signal from high redshifts appears. The square kilometre array is designed in part to conduct these observations. When combined with Webb's optical and infrared mapping of the galaxies responsible for reionization, the 21 centimeter data will provide a complete three-dimensional picture of this epoch that no previous generation of instruments could approach. Let us now talk about something that connects the early universe anomalies Webb is finding to questions about the most fundamental physics of the cosmos. Questions about inflation, about the nature of the quantum fluctuations that seeded all structure, and about what the pattern of those fluctuations tells us about what happened in the first tiny fraction of a second after the Big Bang. Inflation is the theoretical framework postulating that the very early universe underwent a period of exponential expansion by a factor of perhaps 10 to the 60 or more, in a time of perhaps 10 to the negative 32 seconds. Inflation was proposed in the 1980s to explain several otherwise puzzling features of the observed universe: the uniformity of the CMB across regions that would not have been in causal contact at the time of emission without inflation, the flatness of the universe's spatial geometry, the absence of magnetic monopoles and other exotic relics that grand unified theories predict should be abundant. Inflation is not established fact. It is a theoretical framework supported by circumstantial evidence. The CMB power spectrum is consistent with inflationary predictions, but is not proof of inflation. Alternative mechanisms can produce similar power spectra. Inflation makes a specific additional prediction that has not yet been confirmed: a background of primordial gravitational waves generated by quantum fluctuations during the inflationary period that would leave a distinctive signature in the polarization pattern of the CMB, called B-mode polarization. The search for this B-mode signature is one of the primary goals of current and next-generation CMB experiments. If primordial B-modes are detected at the level predicted by the simplest inflationary models, single-field slow-roll inflation, this would be strong evidence that inflation happened, and would constrain the energy scale at which it occurred. If they are not detected at that level, it would constrain or rule out the simplest inflationary models, while leaving more complex inflationary scenarios viable. The early galaxy anomaly found by Webb connects to inflation through the power spectrum of primordial fluctuations. The amplitude of the fluctuations at galaxy scales is one of the parameters constrained by the CMB, and it feeds directly into predictions for early galaxy formation. If inflation produced fluctuations with a slightly different amplitude on galaxy scales than on the larger scales probed by the CMB, a phenomenon called a running spectral index, the predictions for early galaxy formation could be modified without requiring changes to the larger scale CMB predictions. A running spectral index is predicted in some inflationary models. The specific amount of running allowed by CMB data is small, but not zero. Whether the amount of running allowed by the CMB data is sufficient to resolve the early galaxy tension is an active question. Some analyses suggest it is marginally possible that a running spectral index consistent with CMB constraints could alleviate a significant fraction of the early galaxy excess. Others suggest the required running would exceed the CMB bounds. This is not settled. The connection between the Webb anomalies and inflationary physics illustrates how observations of the early universe are probing conditions that existed in the first tiny fraction of a second of cosmic history. The galaxies Webb is finding at redshift 10 or higher are the direct descendants of quantum fluctuations that occurred during inflation. Their existence and properties are sensitive to the details of inflation in ways that can be tested through these observations. Webb is therefore not just probing the first billion years of galaxy formation, it is probing the first microsecond of cosmic existence through the fossil record left in the distribution and properties of early galaxies. This is the deepest scientific connection in modern cosmology. The largest structures in the observable universe, the cosmic web of filaments spanning hundreds of millions of light years, and the properties of the smallest structures within it, individual galaxies and their internal organization, are both direct consequences of quantum physics operating on the smallest possible scales in the first moments after the Big Bang. Webb is reading that quantum record in the light of galaxies 13 billion light-years away. The anomalies in what it reads are telling us that the record contains information we did not know was there. What that information means, what correction to our understanding of the quantum era of the universe is implied by the early galaxy anomaly, is what theoretical cosmologists are working to determine. The work requires combining precision CMB data, precision large-scale structure data, and the new high redshift galaxy data from Webb in a consistent theoretical framework. No such framework yet exists that explains everything simultaneously. Building it is the central theoretical challenge of the coming decade in cosmology, and Webb will be producing data throughout that decade. New deep fields, new spectroscopic surveys, new measurements of galaxy morphologies and stellar populations and black hole masses at extreme redshifts. Each new dataset will impose new constraints. Each new constraint will eliminate some theoretical possibilities and constrain others. The theoretical landscape will narrow. Some of the current tensions will be resolved by better understanding of systematic effects. Others will persist and sharpen. Some new anomalies will be discovered that are currently invisible because the data has not yet reached the necessary depth or area or spectroscopic completeness. The universe is being measured with unprecedented precision. Its history is being reconstructed from the first moments after the Big Bang to the present, with a level of detail that makes the cosmology of 50 years ago look like rough sketching compared to fine-grained portraiture. The portrait is not yet complete. Some of the features are blurry. Some appear to be in places they should not be, according to the best models available. But the portrait is being completed, measurement by measurement, spectrum by spectrum, galaxy by galaxy, across 13 billion light-years of cosmic history, with a telescope that sees what no human instrument has seen before. John Mather's Nobel Prize was for measuring the light of the Big Bang itself, the cosmic microwave background that encodes the state of the universe at 380,000 years of age. His telescope is now measuring the light of the first galaxies, the universe at less than 1 billion years of age. And what it is finding between those two measurement epochs, between the smooth, primordial universe captured in the CMB and the complex, structured universe of today, is richer and stranger and more challenging to the models than anyone expected. The universe is different from what we thought. Not wrong, different, more complex, more surprising, more interesting. A universe that still has things to teach us, despite 50 years of extraordinarily successful cosmological science. A universe that is revealing its secrets not at the pace of our expectations, but at the pace of what it actually is. Webb is listening to it, and it is telling us things we did not know we did not know. There is a specific kind of scientific moment that happens rarely. Not the moment when an experiment confirms what the theory predicted. Those moments are important, but not rare. The rare moment is when a new instrument looks at something familiar and finds it different from what every careful model said it would be. When the data does not fit, when the predictions fail, when the universe turns out to be doing something that the best available framework says it should not be doing. We are living through one of those moments now. James Webb pointed at the early universe and found galaxies that should not be there. Not one or two anomalous objects that might be measurement errors or statistical fluctuations. A population. A systematic excess of massive, organized, evolved galaxies sitting in the light of the universe's first billion years. A time when the models say that only small, primitive, barely assembled structures should exist. A time when the hierarchical assembly of structure should still be in its earliest stages. When dark matter halos, massive enough to host tens of billions of solar masses of stars, should not yet have collapsed. When gas, cooling, and star formation should not yet have had time to produce the organized, luminous systems that Webb is finding in abundance. The galaxies are there, the spectra are confirmed, the redshifts are measured, the masses are estimated, argued over, revised, and still too large. The disks are too organized, the stellar populations too old, the black holes too massive. Something about the early universe is different from what the models say. John Mather, who received a Nobel Prize for measuring the afterglow of the Big Bang with such precision that it established the standard model of cosmology on the firmest possible observational foundation, who then spent years designing and building and launching the telescope that is now challenging that same standard model, said it is a different universe than we thought. He said it with the calibrated surprise of someone who has spent a career thinking about exactly these questions. Who knows what the models predict and why those predictions were trusted? Who is now looking at data that the models do not accommodate? This is not a crisis, it is a discovery. The two feel similar from the inside. In both cases, something does not fit. In both cases, the existing framework is under stress. In both cases, the path forward is uncertain. But they are different in their implications. A crisis is when a framework fails catastrophically, when it produces predictions that are not just slightly wrong, but fundamentally incompatible with observations in ways that cannot be patched. A discovery is when a framework that has worked extraordinarily well begins to show systematic signs of stress at a frontier it has never been tested on before. The stress points to something new, something the framework was not built to capture, something that, when understood, will make the framework more complete. The history of physics is full of discoveries dressed up as crises. The ultraviolet catastrophe, the failure of classical physics to correctly predict the spectrum of black-body radiation, looked like a crisis in classical thermodynamics. It was the discovery of quantum mechanics. The anomalous precession of Mercury's perihelion, the tiny discrepancy between Newtonian gravity and the observed orbit, looked like a crack in the most successful physical theory of the 19th century. It was the discovery of general relativity. The unexpected dimness of distant supernovae in the 1990s, the first evidence that the expansion of the universe was accelerating, looked like a problem with the cosmological framework. It was the discovery of dark energy. In every case, the anomaly came first. The theory that explained it came later. The theory that explained it was more complete, more accurate, and more surprising than anything that had been predicted before the anomaly was found. The anomaly was not an obstacle to progress. It was the path to progress. The universe was not broken. It was doing something new, something that the existing framework had no room for, and that required genuinely new ideas to accommodate. Webb's early galaxy anomaly is following this pattern. The galaxies that should not be there are there. Something about the standard model, something about how quickly structure forms, or about the efficiency of star formation in the early universe, or about the nature of dark matter and dark energy, or about the initial conditions established during inflation, is not capturing what the universe actually did in its first billion years. The anomaly is real. The explanation is not yet known. What is known is that the explanation exists. The universe is not self-contradictory. The galaxies Webb is finding obey the same physical laws as everything else. Whatever they are doing, however they manage to form so quickly, to accumulate so much mass, to organize themselves into such evolved structures in so little time, they did it within the laws of physics that govern everything. The explanation is within those laws. It requires finding the part of those laws that the current models are not capturing correctly. Whether that is a revision to galaxy formation physics within the standard cosmological framework, or a modification to the framework itself, is what the coming years of observation and theory will determine. The coming years will be remarkable. Webb will continue observing for at least a decade, possibly two, with instruments that have already shown they exceed their specifications. Euclid is mapping billions of galaxies to constrain dark energy and the growth of structure with precision that was previously impossible. Raman will survey areas hundreds of times larger than Webb's deep fields, finding the statistical samples needed to characterize the early galaxy population definitively. ALMA is measuring the cold gas and dust content of early galaxies, providing the context that optical and infrared observations alone cannot give. Ground-based extremely large telescopes, the Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope, will characterize the spectra of early galaxies in detail that even Webb cannot achieve for the faintest objects. LISA will detect gravitational waves from merging supermassive black holes and constrain the growth history of the black holes that Webb is finding overmassive in the early universe. All of this data, coming from all of these instruments over the next decade, will make the cosmological picture either more coherent or more strained. The tensions may resolve. The galaxy formation models may be revised in ways that accommodate the Webb findings within lambda CDM, without requiring new fundamental physics. Or the tensions may deepen as more data accumulates and the anomalies become more precisely characterized. The gap between observation and prediction may widen rather than narrow, making it increasingly untenable to explain the discrepancies through model refinements alone. Either outcome is scientifically valuable. Resolution teaches us what the models were getting wrong about galaxy formation physics and sharpens our understanding of how stars and galaxies form within the standard cosmological framework. Deepening tension teaches us that the framework itself needs modification and points toward the nature of that modification through the specific pattern of what the framework fails to predict. The universe that Webb is finding is not the universe that the models built from previous observations predicted. It is more structured at early times than expected. The galaxies in it formed faster and grew larger and organized themselves into recognizable morphologies earlier than the models allowed. The black holes in those galaxies are more massive relative to their host galaxies than the local relations suggest they should be. The stars in those galaxies are older than the available time seems to permit, and yet there they are, in the data, in the spectra, in the photometry, in the morphological analysis, in the statistical excess that persists across multiple independent fields and multiple independent analyses by multiple independent research groups. The universe is doing something in its first billion years that the most carefully constructed models of the last 50 years did not anticipate. John Mather looked at this data and said, "It is a different universe than he thought." He was not claiming catastrophe. He was expressing the honest scientific response to finding that your understanding of something, even a very sophisticated, very successful, very carefully built understanding, is incomplete. That the thing you thought you understood is more complex, more surprising, more interesting than you knew. This is what it means to be at the frontier of science, not to know, to be looking at data that exceeds your models, to be in the gap between what is understood and what is not, building the bridge. The bridge is not yet complete. The data is not yet sufficient to specify exactly what modification to the models is required. The theorists are proposing and the observers are testing, and the gap is being explored from both sides. The bridge will be built. It will be built by the scientists who are working with Webb data right now, analyzing spectra, fitting stellar population models, running simulations, proposing theoretical frameworks. It will be built by the next generation of scientists who will use Roman and Euclid and the extremely large telescopes to accumulate the statistical samples that make the anomalies unambiguous and constrainable. It will be built by theorists who have not yet had the idea that will make the earlier galaxy observations comprehensible within a consistent cosmological framework. When it is built, when the new understanding exists that explains what Webb is finding without breaking what the CMB is telling us, and without abandoning the extraordinary successes of the standard model, it will be a more complete picture of the universe than we have ever had. More accurate, more precise, more capable of prediction at the early times that previous frameworks could only extrapolate to from observations at later epochs. That more complete picture will contain us. The galaxies Webb is finding in the first billion years of cosmic time are the ancestors of the Milky Way. The stars that formed in those early massive structures lived and died and enriched the surrounding gas with the heavy elements that eventually found their way into molecular clouds, into newly forming stars, into the rocky planets around those stars. The carbon and oxygen and iron and calcium that constitute your body were processed through those early environments. The anomaly in the early universe is an anomaly in the history of the atoms that make you. The universe Webb is finding is not a different universe from the one we inhabit. It is the early history of this universe, the first billion years of the 13.8 billion years that produced everything you can see and touch and think about. Understanding those first billion years correctly means understanding the beginning of the chain of events that led to you. The anomaly is in our past. The explanation is in our future. That explanation is being found now, measurement by measurement, spectrum by spectrum, model by model, galaxy by galaxy, across 13 billion light-years, by a telescope that sees further and more clearly than anything ever built. The universe is different from what we thought, more interesting, more challenging, more surprising. Still, after 50 years of extraordinarily successful cosmology, still capable of showing us something we did not expect. That is what galaxies 13 billion light-years away are doing in Webb's data. They are showing us something we did not expect. And that, after everything, is the most exciting sentence in science.